I'm going to talk about is structural dynamic programming models. And that might seem kind of like a niche topic, and I'll explain why it's not exactly niche. But it is a topic, like we've had a lot of talks on machine learning and modeling and simulations, and this is like a topic that lives kind of bridges the two, lives kind of like in the between. So I'm going to first talk about what these things are, why is it, what is it that they address, why we should use them. Then I'll talk about why I think people do not use them, because there are problems with these things. And then I'll talk about why, especially recently, I think these problems are not as big of a deal as they previously were, essentially. So let me jump to what is dynamic programming. Dynamic programming is a way to solve sequential decision problems under uncertainty. So problems where the thing that you do today affects what happens in the future. Got developed by Richard Bellman at Rand back in the 1950s. The story goes that he called it dynamic programming, which is a weird name. So he could hide the fact that he was really doing mathematics, which was apparently theoretical mathematics was frowned upon at the time. Jay mentioned I'm an economist. As an economist, I'm very aware of this because almost all of game theory, modern game theory and modern applied economics rests on dynamic programming. But outside the field, like in machine learning, when I talk to people in machine learning, talk to people who do data science, this is kind of unknown. They say, what is this? Why is this? Why would I be interested? So the thing is, most problems that I run across, and most problems that I think most people run across in this field are necessarily dynamic problems. We have situations where decisions are made repeatedly, and the thing we do today impacts what is going to happen in the future. Those are the interesting problems, whether that's maintaining systems, whether that's procuring systems and then fielding them into the future, whether that's the thing that I worked for a long time on now is how do service members make decisions to stay or leave the service? If I decide to stay today, that impacts what pay grade I'll be in at the next time, what my opportunities in the service or out of the service are going to be next time my contract is up. If there is a reason that service members do not leave service at 16, 17, 18 years of service. They know that if they stay to 20, they're going to hit retirement, right? There's nothing in particular about being in 17 years of service. Like they're looking to the future to figure out what's going on. And if somehow we decided, look, let's reform the retirement system, which we did a few years ago, but let's reform the retirement system to get rid of the cliff vesting of retirement at 20 years, we won't have this pattern anymore. People wouldn't have a reason to continue in service at such high rates at those points in time. So all of these problems are dynamic. And so this is really the mathematical theory of how we deal with them. So let me give you an idea. This is the only slide with equations. This is the only one. I'm not trying to teach people about how to do this, but let me kind of go through it. So we imagine the world is described by a vector of state variables. It sort of collects all the relevant things. These state variables evolve over time. They are different next year and next year, and they're possibly different based on what you do. If you decide to go to school, well, now you have an education. If you decide to invest in a platform, procure more of it, now we have more of that platform and so on. We make decisions, and the payoffs are dependent on the decision we made and the state, right? We value the future usually less than we value the present. And there's some kind of, transition function that governs this entire process. So the top equation says, look, now that you've got this structure, that's the structural part of this, define this structure, bring me the optimal sequence of decisions. And that's a really hard problem because that's a sequence of decisions, right? Bellman did back in the 50s is he took this problem and showed that you can rewrite this as a fixed point problem on the bottom, which looks more complicated, but is actually simpler because you're maximizing over one decision. But that's still a fixed point problem, that the value of a state that's called a value function, big V, today depends on the best thing I can do today, plus the value of the state I'm going to be in after that. And because the state after that is probabilistic, you integrate it out. Now that's still pretty hard. It's a fixed point problem. There's an integral in it. S is pretty big multidimensional. So it's still pretty hard to solve. So why? I mean, I kind of said why we bother, because lots of problems are dynamic, but do we really have to do this, right? Like we could instead do something else, like gradient boosted trees, for example. So let me try to say that yes, we should still be doing this, even though we could do something like a more traditional machine learning approach. So we could take a gradient boosted tree, right? We could say, look, I've got data on decisions, got data on states. Let me estimate a gradient boosted tree that says when the states look like this, make this decision, right? So what does that miss? Well, first, that misses the structure, because that payoff function, if we've specified it correctly, gives us a way to get a causal effect of the underlying variables on the decision. How does this actually work? And this is really not the only way to get causal estimates from observational data, but one of a few ways to get causal estimates from observational data. And once we have causal estimates, we can, of course, do sort of a counterfactual analysis. What if one of our variables was different? Well, do I trust a neural network or gradient boosted model to figure out the real, true causal effect? Really depends on the application. Here, much more so. Second piece is the dynamic piece. Say we have an assignment in the military that's really hard assignment, but if people take it, if you volunteer for it, much more likely to get promoted later. Gradient boosted tree would say people love this assignment. This is a great assignment. That's not true. That's not, I mean, it is in a sense great, but it's because there is a carrot out in the future. We would miss any of the costs or consequences of our actions if they're in the future. And often that's kind of a really important piece of the costs and consequences that we're talking about. So that's the two pieces we would miss with something like neural networks, gradient boosted trees, old OLS, and so on, and why we sort of should bother with this. So let me give like an example, and I'll come back to it in a little bit. But let's suppose we have a maintainer. Maintainers got to decide, do I replace, and same for maintenance, a GCU of an aircraft or not, right? GCUs fail notoriously often. You can pull it off every however many hours, send it for maintenance to the depot, get it back, or you can wait until it actually fails. But if it actually fails, you're supposed to fly the mission, you're not flying the mission, right? So a maintainer has to decide based on the hours this GCU's been up. So I replace it or not. If I replace it, great, I gotta pay for it. If I don't replace it, nature gets to flip a coin and we either go to mission capable aircraft or not. And then we do this again tomorrow, and then we do this again tomorrow. Very straightforward dynamic program that should be pretty easy to solve. And it's pretty easy to solve. So suppose we got it. We got data on what maintainers actually do, and we go through and estimate this model. We'll specify some kind of payoff functions here. They're very easy. I just put something up there. But this is where machine learning kind of actually comes in. We could make these very complicated. We could say that this payoff function is actually, say, a neural network of all the states, say. So we could make it probably a tree. I don't know how to implement a tree here in the middle of this algorithm, but I'm pretty sure it's possible because it's just an arbitrary function. So however complicated we want to make it, but it lives inside of this dynamic programming structure. And so we say estimate it and figure it out. So what can we do here? Well, like let's say, for example, reliability of the GCU went up 10%. What's going to happen? Well, it's not true that failures are going to go down 10%, because the maintainer knows the reliability went up 10%. The maintainer now has a less of an incentive to replace the GCU because he incurs a cost every time he replaces a GCU. So he might take this as if there's not sufficient penalty to it, might take this as an incentive to keep GCUs that are marginal on the aircraft more. So is it true that we necessarily have fewer failures of GCUs on the flight line? No, it's not actually true, because you have to account for how people make decisions. Here, people make decisions looking forward to what's the cost that will get incurred if I do not replace this GCU. We just lowered that cost of what happens. It's very, I mean, depending on exactly what the costs are and how it balances out, we may have more, like there might be more time between failures, but we might incur more failures on the flight line when you go to spin up the GCU, doesn't work. And if that's the critical piece that we are interested in, being able to fly the mission when you have to go fly the mission, then this is how, like, then this reliability, this specific improvement might not get us what we want. And we would miss it otherwise, because we would miss this entire what happens in the future piece. So these are great, but why do people not use them? Why do people in machine learning world, for the most part, have never heard of these things? Well, they're very hard, right? I showed you the fixed point equation. When S is multidimensional, it's a really, really hard problem to solve. And in order for the model to be useful, S has to be pretty multidimensional. The rest of the talk talks about how do we get around it. But before I get there, let me talk about the realism and tractability piece. Actually talked about, well, you can just throw 700 odd things into a model and let it sort it out. So I have sort of, and I'm an econometrician, I got trained this way, but I have sort of a view that it is important to stop and try and figure out how the process we are modeling actually works. What are our objectives? What are our constraints? And that this part of sitting down and writing a parsimonious model that captures all the relevant information that we need is actually really important. Now, might be true that it still has 700 variables, but it might be true that we still want to estimate a non-parametric arbitrary function of them. Have to be convinced that yes, we really, really need it, I think. So, but that aside, now let's talk about, well, we would like these things, they look good, but to make them realistic, we've got to have lots of, they have to be complicated enough to be realistic. They've been popular in academia for a very long time, but usually they're very simple when they're estimated, even back in the 80s, right? Like a lot of this work started back in the 80s, computers became much more prevalent. People would estimate, but they would estimate the really, really basic models to demonstrate that, an effect exists, but you wouldn't make policy off of those things, right? Like they were not complicated enough to capture the salient pieces of the real world. Now, I think with the things that got developed in the last 20, 25 years, we can relatively easily estimate models that do capture those salient features of the world. So there are three things that really sort of changed the way things go. One is just computing power, right? Like I've got more computing power in my laptop than Hopkins department had 20 years ago for the entire department, probably, right? Like there's just an enormous availability of computing power that is freely available to us. If your computer is not enough, there's easily available cloud computing, right? Like there's just raw power that's massive. But in addition to that, people have, with a focus on ML, developed approximation methods and econometric algorithms that really help solve this specific sort of dynamic programming setup problem. I'll talk about them in a bit, but I also have their computational advances, right? Like everybody read about Go being solved by Google's AI, right? And I have solved there in quotes because I actually think that's kind of a good illustrative point to what we want to be able to do versus what machine learning models attempt to do. So if you think about, I don't actually know how to play Go, so let me talk about chess, right? If you think about chess, it is a dynamic program, right? There's a state is described by where the pieces are at the board, and you want to make the best decision. Obviously, what you decide affects what's going to happen in the future, right? Clearly a dynamic program. It is solved, right? Really solved by AI. What we usually want to do in policy isn't to answer the question of, given this distribution of pieces on the board, what should I do? It's usually already solved, we usually know. What we want to do is, suppose the rules changed. Suppose the bishop can now jump over other pieces the way the knight can. Now what should I do? Right? Suppose that there is a new capability that an adversary has. Suppose I have a new capability that it didn't have before. Suppose there's a pandemic. Suppose there is, rules just changed. Now what do I want to do? So that's why you need the structure. That's why you need all of those things that we talked about to be able to answer a question of, now that the world's different, what do I do? Machine learning is really great, right? Forecasting. Sometimes we really do just need the weather tomorrow. Right? Sometimes we really need to know how many seats do I need in a training, right? That's exactly the right application for the right tool. Sometimes it's not. So that's why solves is in quotes. Somebody in a previous time I ran through this points out, like, why is it in quotes? It's in quotes because, yes, it's solved in a sense that we know what to do this way, but it's not like the computer understands the rules and can sit there and think about, oh, great, now that the rules are different, now what do I do? You have to start essentially over, train it from scratch with a new set of rules. But let me now talk about approximation methods and econometric methods, and we'll circle back to the GCU example. On approximation methods, this is really old idea, but it was not really possible, feasible until about, I don't know, 15 years ago or so. You think back to that fixed point problem, we got value on the left, value of the state on the right. Fixed point problem, kind of hard to solve. Well, let's take the one on the right-hand side, parameterize it somehow with a sufficiently flexible arbitrary function that could map the state to the values, right? What does that sound like? That sounds like machine learning. It's exactly what it is. Let's plug in a neural network. Let's plug in something else, an arbitrary polynomial, some other non-parametric interpolation function into there, and let's go ahead and estimate. Used to be very, very hard to do, not terribly practical, but now with all of the machine learning toolkit that we have in Python, in R, use Keras, use GPT, use whatever you want, and go ahead and estimate. Not suddenly, right? Like instead of having to write the algorithm yourself, trying to figure this out, suddenly it takes 15 lines of code to go ahead and do that. And you can get an approximation that's almost as good as, it is a solution because, you're solving for the value of the state, but using the approximation on the right-hand side. And now, like that's very, very typical of the kind of things that we can do. Second one is similar. In econometrics, right? Like when we're doing inference from data, biggest headache that we always have is, well, there's something not observed that's persistent that's affecting what is happening, right? Really capable service members get trained on, get sent to special training, and therefore they're more effective later on. Do this and you say, oh, great, the training really, really works. Well, we only send really capable people to the training, but we don't see how capable they are ahead of time. So like, maybe it works, maybe just a selection process, right? Like economics, this is the like people go to college, but like people who go to college and don't go to college are very different people. So the returns to college look really great on paper, but you're not comparing apples to apples. So like, what do you do? Again, solutions sort of been known, statistically speaking, for a very, very long time. You have to specify a distribution of that thing you do not see, and then you have to integrate it out. It's not observed. Very easy on paper. Statisticians have all sorts of theorems, right? Just put a couple of integrals in front of your thing and it works out. Very, very difficult in practice because you're saying, great, take a numerical integral of this massively multidimensional thing that's actually really complicated to evaluate. So that's a very, very hard problem. But again, we have now a lot more algorithms, well, both computational power, but also approximation algorithms that do allow us to take good approximations of those integrals and to, yes, incorporate this kind of unobserved heterogeneity into the models that we're dealing with. So for the that's this GPU, GCU control unit, not different. But like the initial model was clearly too simplistic, right? Nobody's going to make policy off of it. Nobody's going to use it in practice. So what would we need to do to make it useful? Well, let's add more information about the aircraft, when it was made, how many total hours it has, what conditions it's been flying in, more information about the mission and the kind of performance it has had, what phase of the readiness cycle are we in, how much maintenance has been done. The payoff structure can depend on actually the criticality of the mission. It's entirely possible that maintainers on deployment, I'm thinking of Navy because Jay said I've worked at CNA for a long time, but on deployment, maintainers are probably a lot more careful, right? Like a failure of the flight line to launch it from the carrier is a lot more costly than a failure, during maintenance phase, whatever, you've got to get your hours, but to get them today, to get them tomorrow, it doesn't matter, right? Like the cost is massively different. There's actually 2 GCUs, so, there's all sorts of complications. There's also complications of some things are not observed, like Maintainers will tell you some aircraft just duds, right? Like that one always breaks. Like, okay, well, there's an unobservable gremlin there, right? Like that's okay. You can incorporate that. You can incorporate past service history that you might not see and so on. Suddenly this sounds, oh, this is really, really complicated. No, we can estimate a model like this, like probably on my laptop. If you were willing to specify it, if you're willing to incorporate all these pieces, use machine learning techniques that we've all heard about for 2 days now inside of it, yeah, you can go ahead and estimate. It's not nearly as prohibitive. 20 years ago, this would be a non-starter, right? Like 20 years ago, you would bring this to somebody and they would say, no, we got to strip all of this out. Today, not so much. Today, we can absolutely estimate this model without too much effort. And my point is that we should. My point is that in defense applications, we have so many things that require these kinds of dynamic programs, right? Whether it's investment in a platform, right? Like, do we develop the platform, we procure the platform, operate, sunset it? That's clearly a dynamic program. And we don't usually treat it that way. Personnel policy is a dynamic program. When do we incentivize? Like, who do we recruit? How do we recruit them? Where in the career do we structure bonuses? How much obligation has to go with it so that we have the right service members at the right point doing the right things? That's a dynamic program. Strategic competition with an adversary is clearly a dynamic, repeating dynamic, infinite horizon game. And yes, there's been some work on it in sort of political science, military science type of settings, but it's usually very, very simplistic. And we can do much, much better. And when we don't, like what we're missing is those like, yeah, 5 minutes. I'm going to finish in like a minute. But what we're missing is the future costs and future benefits of the actions. And in these dynamic settings, that's pretty much all that there is to it, right? Like what we're doing, if we use just a straightforward model like we often do, is we get a static approximation, which assumes that those future things are basically zero. And in these cases, those future costs, those future payoffs are really, really non-zero. They're really, really non-trivial. And so hopefully, those of you who do work in, I don't know, places where there are dynamic questions, like look into all of it, get in touch with me, get in touch with other people. But like, I absolutely think that this is the sort of things we should be doing. I guess we got 5 or 4 now minutes for questions. Thank you. Yeah.
So whenever somebody starts talking about counterfactual reasoning, I start thinking about counterfactual reasoning with uncertainty. So for example, in your chessboard example, suppose you can't actually see where all of your opponents
Absolutely.
are. How does dynamic programming, or how might you approach that kind of problem with dynamic programming? You put those in as unobserved variables, or what's the
right? So there are 2 different things. There's 2 possibilities of how to deal with it. If these are things that in the past we have observed, right? Like that sort of, we just don't know what the future will be like, but we're not certain what will happen, what move the next person will do. But in chess, right? Like I'm not 100% sure what my opponent will do, but anytime it comes time for me to make a move, I do see the board, right? That's relatively straightforward. That is uncertainty in forecasting too, right? It's like we can enter different values essentially, like here's my low forecast of what future holds, here's my high forecast, and I can give you intervals. I think what you are talking about, and is the more interesting problem, is that often we do make decisions when we don't exactly know what even the current state is. We don't know the future for sure, but we don't really know the current state, right? Like think of wargaming, right? Like there's fog of war. I'm literally playing chess, not really sure where the other person's knight is. Yes, the process is really that you treat it as a random variable and you do integrate it out. You specify a distribution, maybe you know an empirical distribution you can use. If you really don't know, you specify a hopefully appropriate one. And when you're making a decision, when you're solving that problem, there's uncertainty about something in S. So there's an integral out front of this problem that integrates with respect to S, and there's a distribution. That makes it harder, right? This is very, very similar to the like, I don't observe people's ability, so I need to integrate it out. Don't observe exactly what something is going on. But so this is exactly the big interdimensional integral. It is hard to do computationally, but yes, we have approximation methods, and frankly, we have enough computing power to just go ahead and do it now. I think that, again, 20, 30 years ago, people would say, absolutely not, you cannot do this. You must assume that you know this thing, or that's it. But yeah, we can incorporate this kind of uncertainty. That's entirely doable. Anybody else? Yeah.
Typically, people have a hard time relying on models unless they're verified or validated. So presumably to validate a model like this, you have to follow a strategy that is predicted by the model and then show that you're getting the predicted outcome. So how would you go about convincing someone to follow a model like this without having them explicitly follow the model?
That's a good question. So if it is a model of something we have not observed before, right? So like there's sort of two different, one is inference, the way we usually do machine learning, right? And this is a kind of machine learning. I want to understand how service members make decisions, right? I have data on service members, I have data on their decisions, I estimate this model, I can validate it in the normal way, right? With a holdout sample, and it predicts that the service members will make these decisions. They correspond to the decisions they actually make. Fantastic, it's close, right? It's never going to be 100%, but it's close. Now, what do I do if I have a model of something that we have not ever really done before? That's where a lot of SME input, frankly, comes in, because at that point, this becomes sort of like an OR. There was a NASA talk yesterday, right? Like not quite physics model, but if you were at that talk yesterday on trust in AI, this really isn't that different from that physics model that he was talking about. Like that this is sort of from first principles. If we're talking about failure rate of a component, well, maybe I have some of these different things that go into the transitions. Like maybe I do observe some of them, right? Like I do observe failure rate for a component based on the number of hours it flies. Like that's an objective thing. I'm going to take that. I'm going to take, the number of mishaps that happen when you try to spin up, or not mishaps, but the number of actual failures when you spin up the GCU. Like I'm going to put that in. So I'm going to build it basically from first principles that I do know about and can learn about and estimate. I'm going to squish them together. And at that point, there is a sort of leap of faith that once all put together appropriately, it will tell you the right thing. But if you're talking about the physical thing, but also if you're talking about the way people will behave, strategic adversaries will behave. If you don't have data to learn from, like, right, game theory, economics, econometrics, operations research can tell us sort of, we think they will behave this way, but it comes to people, right? Like without data, I think that relying on first principles, this forces you to write it down. Also, I do like this better than machine learning in some sense, because this forces you to write all of this structure down. And somebody says, I don't trust your model. You can say, great, like which part do you not trust? Right? Like, oh, you think the transitions should be different. Like, okay, like let's talk about it. Like, oh, you're the SME, great. I don't know really about aircraft maintenance. Let me put in the right thing. Or like, I think this payoff's not big enough. Like, all right, like, cool, let's change it and adjust it. Machine learning black box? I don't know. But here, this is start to finish, all of the assumptions. If you say you don't trust the model, don't believe it. Like, I mean, a high level stakeholder might not, but if you're talking to a sort of practitioner, you can say, great, like which part do you not believe? Let's talk about that part. Let's fix that.
Question regarding the payout function.
Sure.
So if you were to do this in practice, you would have a sample of the decisions that you did make, but you can assign costs or payoffs to those. So how do you assign a cost or payoff to the decisions that you didn't make? The only way to really know is to have that sample? Is this like defined ahead of time for every single decision we define a cost, or?
Well, not entirely, kind of. But we do see people who, assuming, make different decisions, right? Like, so if I'm here and I have never seen a maintainer not replace a GCU, then I don't know, right? If I've never seen something happen, then like I do not know, right? Like it could have a giant cost, could have no cost. But some assumption here is sort of that at some point I have seen maintainers not replace a GCU. If I'm considering service members staying or leaving, certainly the ones who stayed didn't leave, right? Like here they are. But some others did. And I can figure out their problem and I can write down their problem, the problem they must have been solving in this way. So if I stay, I get to do this job, I'm likely promoted, 15 years, I get retirement. If I leave, I get to go to, maybe I have my GI Bill, I get to go to college, I can settle down, have a family, and have a job that pays this much. 80% pick this, 20% pick that. All right, make inference based on that and what kind of payoffs each one of those things must be. Make sense? Like if I've never seen somebody leave, I don't actually know anything about the value of leaving. It could be 0, it could be negative, it could be anything. But once I've seen some people do it, I can make statistical inference about it.
Okay. So to model this to my specific problem, I have to know all the possible decisions that I could make with my problem.
Yeah, sure. Yeah, no, you do have to know the set of decisions that's possible.
Okay.
Yeah, because you're going to have to characterize it in some way. Yes. It's going to be hard if you don't know all of the, well, actually the state space too. You should be able to characterize this. You might not know the functions, right? You might not know what U is. You can estimate it. You might not know what P is. Estimate it, learn from the data. But you do have to be able to tell me the rules of how things work. You might not know what values these things take, beta, right? You might not know the discount factor, can estimate it, that's fine. But yeah, you got to know the things, the decisions. But in machine learning too, right? The target variables, the Y's, you got to know what those are. Got to know the X's,
So yeah, I'm trying to figure out how to frame the problem.
No, but I'm trying to draw parallels to things you might not know better, yeah.
I think describing it as rules.
Yeah.
Figure right out.
Yeah, people talk about this as structure, but yeah, this is the rules. In game theory, they would call this rules, right? Like, but it's not just game theory. Sometimes there's no game. Anybody else? Yeah.
Semi-follow-on question to that. You talked a little bit earlier in the talk about now you're talking about open STDG. What are the restrictions? And this, I'm assuming this is going to be from the computational side on what you can put in to do. What can that function look like? What can't that function? But could I just say I want to draw from some arbitrary distribution as you?
Yes, you can. I think the constraint is largely computational. Certainly, but so there's no theoretical constraint, right? Like it can be an arbitrary non-parametric function of however many variables you want. Practice, that really depends on how much computational power you are bound by. You can include, well, the problems are so different, right? Like in my example of estimating a decision of service members stay or leave, right? So that decision, that's multiple decisions for 30 years of a career. I've got samples of thousands, hundreds of thousands of service members. We usually include 2 to 3 dozen different things that go into the U function in every period. It can be nonlinear. So things that are not categorical can be nonlinear. We find that sort of fits really well. And at that point, we sort of don't see the need to make it more complicated, but certainly can be. Yeah, Jay?
So if you're using this for, to follow this, so if you're using this for estimate the causal effect of something.
Yep.
You do at least need the function used to be such that you have identification of
This is true.
the parameter that you're trying that tells you about the causal.
this is absolutely true. So if you are an econometrician and you worry about causal inference, yes, you must have, that function must be identified. So you must have some kind of variation in the underlying parameter to identify it. Most of the identification, if you are saying that the function u is, continuous or close enough to continuous, and continuous variables has derivatives, exists for the most part in the right place, right? Like, so there's all the sort of normal caveats to it, that it really is a function, and the data vary sufficiently, then for the most part, these things are identified. There's sort of a whole literature on non-parametric identification there. But for the most part, it's pretty hard to separately identify the discount factor. You do need to observe the same people facing different decisions over time to identify the discount factor. So in many applications, people just put something in, right? Like from surveys or from other research, we know that people discount the future when it comes to money 5 to 7%. So very often we will just put that number in there with a appropriate citation. So that one is a little bit trickier. The function u itself is, for the most part, even when you have an unobservable variable in there, is for the most part identified non-parametrically. So as long as the thing you're talking about really is a function, it doesn't have point discontinuities, it doesn't have other very weird things going on, you can go ahead and estimate it.